Hi, everyone. My name is Shomo, and this is going to be a brief talk on my research interests and what I like to do and what excites me about my research. I'll quickly share my screen and tell you about my current research interests. What I do is I build computational models, especially machine learning tools for complex systems. And over the last few years, I've worked closely with domain experts and stakeholders in a wide variety of disciplines and applied machine learning tools to their unique problem sets. And I've worked very, very closely with them to deliver these solutions. So I'll just quickly step you through some of these solutions and some of these unique problems that I've worked on. One of the first things that I want to talk about is I have built what are called hierarchical Bayesian models of viral infection. Now, these were sparse time series data that were collected from different species that were infected with a known viral strain. And then there is a dynamical model, a nonlinear differential equation model that captures the arms race between the immune system and the virus. And the idea is that we have to infer how fast is the virus replicating in each of these species. And the way we did that is there was this dynamical systems model, and we had prior information on some of these parameters. Some of the parameters tell us, for example, how fast is the virus replicating, how fast is the immune system responding. And we built a hierarchical Bayesian model that allowed us to infer some of these viral infection parameters and immune system response parameters. And the hierarchy came from the relatedness of different species that were infected with this virus. In sort of more recent work, I've been very, very interested in applying machine learning techniques to rich data sets that are coming from electronic healthcare records. And that has to do with practical aspects of dealing with sort of audits and building sort of sending reports to sort of ethics committees, looking at anonymization and security procedures. And then ultimately, once we get data access, building machine learning models to stratify patients or predict some kind of disease outcome. And these can be linked to definitely next generation sequencing data. So one work that we did in close collaboration with clinicians is where we took sort of patient microbial samples from different cohorts of patients and use them to sort of predict disease status and what kind of microbes are present in these patients. This was again building a statistical learning and machine learning framework to sort of predict outcomes and disease severity status. Even more recently, what we have done is, again, working closely with clinicians, experimentalists, and HPC folks. We have built informatics platforms and machine learning tools that can take in electronic healthcare record data, marry it with single cell sequencing data or bulk sequencing data, and then use that to classify disease severity. So here is one of the machine learning model outputs in a large cohort of patients. So rows are genes, features that have come from single cell sequencing and other sequencing modalities. And the color of this heat map shows you what's the likelihood that these patients would get a severe disease in the future. So again, this is using machine learning models to predict disease severity. Again, huge amounts of data that we dealt with coming from electronic healthcare records and also other sort of data modalities like single cell sequencing, bulk sequencing, microarrays, and all of that. This was done in very, very close collaboration with clinicians, experimentalists. I also worked very closely with the pharmaceutical company. So one theme that runs through my research is I really want to embed myself. And this is what I also want to teach my students is how do you embed yourself in distributed teams working in completely different domains, but then delivers a solution that really solves a problem for them. So we worked very, very closely with a pharmaceutical company in this, and even in the other project that I mentioned. In another recent project, we have again looked at electronic healthcare record data, and in sort of psychiatry and severe mental illness, in particular schizophrenia, which is a severe mental illness, and derived features from electronic healthcare records, and then used a deep learning model called an autoencoder to sort of use that to first stratify patients. And then on top of that, we built another sort of random forest model to predict disease outcome. And a recent focus has been interpretable machine learning. That is, how can you take these black box machine learning approaches and make them explainable or make them interpretable. And in this case, we used a technique called class contrastive reasoning to really make sure that we understand what are the predictions that these deep learning models are making and how can we understand them. And for example, we can understand these using a simple heat map that we derived called a class contrastive heat map that shows us what is the effect of changing one or even more combinations of features on the model output. Again, this was a project done in very close collaboration with domain experts like psychiatrists, and there was a lot of machine learning models that had to be built, a lot of practical data aspects of getting access to the data and doing data munching, and really also understanding the domain. This was a completely different domain of psychiatry and severe mental illness. Another project that I would like to talk about is where we worked closely in a completely different domain, in this case, supply chains and logistics. We worked closely with a national laboratory in Australia and several companies in Sydney and Melbourne, where we understood how the supply chains and logistics actually function, built a detailed stochastic simulator of how, for example, goods are sent from one depot to another location, and then there can be multiple modalities of transportation like train or trucks. And we really wanted to understand, using commercial data that they had, how can we streamline their sort of supply chains. And this was done in very, very close collaboration with industry experts and even DevOps people. There was sort of a machine learning angle to it, using forecasting to sort of forecast future demand, building stochastic simulators to sort of simulate the internal dynamics of how supply chains really work, and also building an application that can be used by these companies. So I also have experience, and I love working with sort of practical software engineering people who like to build sort of real world applications. And one sort of output is from this kind of work can be, for example, this is showing the greater Sydney area and what kind of cost, sort of attractiveness, and what kind of bottlenecks there might be in sort of supply chains. These were in fact direct inputs to various stakeholders, including companies and government bodies who were very, very interested in streamlining any bottlenecks. So I do have a lot of experience working with different stakeholders and applying machine learning solutions and developing machine learning solutions with them. One of my career goals is really developing computational models and machine learning models for complex systems. As you have seen, I have worked in a wide variety of complex systems, ranging from healthcare, biological systems, and supply chains. And what I really like to do is build sort of computational models that allow different domain experts to solve all of these problems. And I love working with these domain experts And really one of my goals is to have a faculty position ultimately that allows me to solve these kinds of problems. Here are some summary of my skills, naturally machine learning and statistical learning experience, and I do have extensive programming experience in R, MATLAB, and Python. I've worked in industry before, and I continue to work closely with industry. And I absolutely love working with sort of industry experts, domain experts like clinicians, experimentalists. And I'm quite keen to work on, for example, sort of emerging domains like machine learning applied to the physical world. This is sort of my research and teaching philosophy. As I've said, I'm really keen on working with domain experts and building machine learning models in close collaboration with them. And this is something that I also want to teach my students. That is, how do you sort of take a problem, go into a completely different domain area that you have no idea about, but work very, very closely with domain experts, be really invested in their problems, and then deliver a solution. So I really want to teach practical skills to my students on how to apply machine learning techniques to sort of different domains, especially emerging domains like in the physical world, for example. And this really informs my research as well as teaching philosophy. And this is something that I'm very, very passionate about, working closely with all these experts, working on exciting problems. Here is a link to my website. Please take a look through that, and you can take a browse through my papers and software that I have written. And if you have any questions, please get back to me. Thank you so much for your time. Thanks a lot.